So what we have here is we have a metallic strain gauge, all right, that's measured, that's placed on a simple rectangular bar that's 30 millimeters wide, all right, by 10 millimeters tall, all right. All right. So we are applying a 30 kilonewton load, all right, to this bar on both ends, all right. And we're told that the bar is made out of steel. All right, so the bar has a uh, Young's modulus of 200 gigapascals. All right. So the first part is we're going to determine the change in resistance uh, of the strain gauge if the resistance of the strain gauge is 120 ohms when there's no load. All right, we're also going to assume that all of our resistances are 120 ohms. All right, and the second part of the problem, I was going to ask if we can only measure an uncertainty of about plus or minus 5 ohms, plus or minus uh, 5 milliohms, and we have a resolution of about 1 milliohm. What would be the uncertainty in the stress measurement that we're using? All right, so let's look at our change in. Let's first determine the change in resistance. All right, so we know the relationship, all right, as being equal to delta R over R divided by 4 is equal to the change in the output voltage over the input voltage. We also know that the change in the output voltage over the input voltage we can relate to the strain for a single gauge. If we know the gauge factor, the axial strain, and we know and we divide that by 4. Okay, so we're going to ignore this component in the middle here, and we're just going to solve for the delta R. All right, so we can say delta R is going to be equal to the resistance times the gauge factor times the axial strain. So we plug in the values that we know. All right, so we can say that the change in resistance is equal to 120 ohms. The gauge factor is just equal to 2. All right, and then the axial strain. So the axial strain we're going to have to determine using Hooke's law. So we're going to say the axial strain in this case is it's simple 1D should just be equal to the applied stress over the Young's modulus. So the applied stress in this case is the force over the area. All right, and then our Young's modulus is E. All right, so we're going to plug in that to our equation down here to solve. All right, so our force we were given as being equal to 30 times 10 to the 3 newtons. All right, the cross-sectional area would be the base times the height. So we were given 30 millimeters by 10 millimeters. So we're going to write that in terms of meters just to keep everything in the same. So it'd be equal to 0.03 meters times 0.01 meters here. All right, and then we divide that all by the Young's modulus, which was 200 times 10 to the 9 newtons per meter squared. All right, so basically all the newtons in the meters squared terms cancel each other out, and we're left with, if we multiply all this through, we get a grand total of 0.12 ohms as the total change. Okay, so very little change in our resistance. Okay, so all right, now in the second part of our problem, we're asked to determine what is the change, the uncertainty in the stress measurement that we could determine using this device. Okay, so we're going to rearrange our equation a little bit here. All right, so we take the same equation we had before. All right, so for part 2 here. All right, what we're going to look at is we're going to look at delta R over 4R. All right, is going to be equal to, all right, our gauge factor over 4 times our stress divided by our Young's modulus. All right, now, all right, we're going to rearrange this equation here and solve for our axial stress. So if we do that, it's our axial stress in this case would be equal to our change in resistance over 4R times our times 4 divided by our gauge factor times our Young's modulus. So the 4's cancel out, and we're with delta R over R times our gauge factor times our Young's modulus. All right. So we can say that the uncertainty, if we look at the uncertainty in our stress, we can define it as being the partial derivative of our axial stress with respect to the delta R measurement, all right, times the uncertainty in our resistance measurement. Okay, so what we're going to do is we're going to take the partial derivative of this term with respect to delta R. That's really simple. It just becomes 1 times E over R GF. All right, and then our uncertainty and our resistance was given in the problem statement as being equal to 5 milliohms. Okay, so we're going to just leave it as 0.005 ohms. All right, so if we plug in all our terms, all right, we solve our equation. All right, what we end up getting is we get 200 times 10 to the 9th newtons per meter squared over the resistance, which was 120 ohms, times our gauge factor, which was 2, all right, times our uncertainty and our resistance, which was 0.005 ohms. All right, now that uncertainty ends up being 4.17 times 10 to the 6th newtons per meter squared. All right, so about 4 megapascals. All right, now if we're interested in the relative error compared to what the stress would be, all right, or the relative uncertainty, all right, what we can take is we can divide that uncertainty and stress divided by the stress in the axial direction, and then we can say, so we know that the axial stress, or the uncertainty was 4.17 times 10 to the 6th newtons per meter squared, all right, and then the uncertainty, the stress that was given, right, was 30 times 10 to the 3rd newtons divided by 0.03 meters times 0.01 meters. Right? So if we do all of these calculations, what we end up getting is about 0.0417, which is about 4.2% error. Okay. So what we're trying to say, if we look at the top part of our equation of the video here, if we look at the diagram here, what we are saying here is that if we're applying a load, all right, and we're using the strain gauge to estimate the stress within this section, based off of the uncertainty in the resistance measurement, we would be, for the given stress that we were applying, we'd have an uncertainty of around 4% of what the stress measurement is. So that's not too bad, really, if you think about it, right? Most of the time when we're designing things in engineering, we use like factors of safety, which allow us to apply like 2 to 3, sometimes up to 5 times the amount of load that we expect to apply. So what this is saying is that if you can measure the stress within a component using the strain gauge method, using a strain gauge, is that you can properly determine what the stress is within that specimen under the applied load, and it gives you a good approximation of a good estimate of what the current stress is in the component, and you can use it to predict failure and validate your prototype.